Welcome everyone to the 19th edition of this distinguished lecture series. Today we have Mr. Cachin, and we're very happy to host him. Christian has a PhD from ETH Zurich, and he's taught at several universities. And for over 20 years, he was at IBM Research Zurich, but since 2019, he's professor at the University of Bern. His research areas are mainly distributed systems, consensus protocols, cloud computing security, and he's also authored a textbook on the subject. And today he will tell us about recent developments in consensus mechanisms as they're applied in blockchain protocols. Let's join me for a warm welcome.
Yeah, so thank you for inviting me. Thank you for running out of chairs in the room. It shows that Vienna is a blockchain hub next to Crypto Valley in Switzerland, apparently. But it's true that we are working. So I have been working in cryptography and in distributed computing. And if you do both of these things today, then you must be working in blockchain protocols. Right? It's just too good of an opportunity. And I hope to give you a bit of a background and overview of blockchain consensus methods. I cannot be very specific in the allocated time. And then I would also, yeah, actually, John, no, it doesn't work. Okay. Okay. This is the plan here. I first would explain a couple of models that have all been used for consensus in blockchains. And then we can go talk about certain results that have come out of the research in my team in Bern now, since I've been at university. While I was at IBM Research, I did things like Hyperledger Fabric in this space, which has become very popular, but I'm not going to talk about this today. And at any time, feel free to ask questions, and certainly at the end, you'll have more time for questions. Yes, so models. There are many models in which blockchain protocols have been defined. And there is a huge spectrum of those models. And my current idea is to give you some overview and some insight in these models. What is a model in consensus, and especially in blockchain? It's about the trust assumption that is used to decide in the blockchain, basically, or in a distributed system, more generally speaking, on what is valid and what the system does. Threshold trust is how we have known this from 40, maybe more years ago, from Lampert and others also. Leslie Lampert coined the term Byzantine agreement. So you are today talking about Byzantine fault tolerance. This means what Lampert formulated as a model, what is shown here, that I call today threshold trust. In distributed computing models, like often in theory, we make some slightly innocent assumptions that turn out to be showstoppers later, or that disconnect us from a large part of the rest of the world. In the blockchain space, in the distributed protocol space, Lampert says clearly if we have a system of disconnected nodes that talk to each other and should do a common job, there are going to be n nodes, and each one can vote. Yeah, and we know who are these n votes. Turns out that this model is very useful for certain things, but it's not useful for the approach that Satoshi Nakamoto wanted to pursue when he built the first peer-to-peer cryptocurrency, Bitcoin, that works without these types of votes, because they did not want to be identified. So a prerequisite to this model here is that you can identify who are the nodes in the system. And many systems use this kind of approach. It's also clear that in this approach, that's been going on for a long time. A lot of deep theory exists in this model. We are going to vote. We're going to vote as a Swiss. Voting has been enshrined into my genes, probably. Not that my family root has been Swiss for centuries, but long enough so as not to remember how one could do things differently. There are chairs in the back and in the front, so you should go there. There's also one in the front. So the voting thing is what we do. And if the majority decides to do something stupid, it's what the system does. Yeah, we are going to assume in some other form that they're not going to decide too many stupid things. In this model here, we are going, so the model of distributed computing that has been explored for decades until the blockchain revolution actually used this as its basic assumption for the protocols. There are these n nodes, and each node has a vote if you're talking about like systems that tolerate inside corruptions. And then we tolerate also timing uncertainty. And for tolerating the malicious ones and the timing, we need a strict 2/3 majority. So n bigger than 3f is what's shown here on the slide, is a prerequisite for doing something useful in this model. It may also be the case that you do not reach, that you make not progress here, because if you're having a simple majority, either yes or no gets a simple majority. If you need a strict 2/3 approval, you can also get to no decision. Whether this happens or not, let's postpone the question. In the blockchain world, this has not been the most prominent model in the past, but there are some notable chains, like some multiple systems that have started to build on this. For example, the Tendermint software library that is used in the Cosmos ecosystem is the most prominent code base that uses this type of decision model. So the nodes make progress by voting, and they can tolerate a minority, but not more. EMBFE, for those who remember, Facebook wanted to do a cryptocurrency. They do not want to do this anymore. But while they were doing this, they were also following this model. And then Quorum is another blockchain. Because this is inherently linked to so-called quorum systems, we'll talk about them a bit later. Because a quorum is what? A quorum is mainly a majority of the voters. So it will be f plus 1 if you have 2f plus 1 and it's 2f plus 1. Turns out that this is in some sense restrictive because now everybody has the same voting power. And in the theory of distributed computing and cryptography, we have long explored a different model that is somewhat like this, but not exactly. We call it generalized trust here in this context. We actually, the ones that formulated this goes back to Malky and Reiter and also to Maurer and Hirt around 2000 and in the late 90s, when they were realizing, oh, we can define arbitrary sets of participants that have the power to decide. So one person can be more important together with others, or maybe less important together with some others. Just like in real world companies, you have some power structures that are not just by number, right? They are the boss is more has more power than the subordinates, but the boss in certain situations may have less. So they have different voting powers, not only additive, but more generally speaking. So we have, in this model, we are going to define, we're going to take a different approach. We're going to say, whom do we want to tolerate in the system? In the previous model, this was an assumption that we tolerated all sets of faulty sets. We tolerated, the system remains okay, even if any set of 2 nodes were corrupted. Here in this case, we let you the flexibility to define these sets of possibly corrupted nodes. And in an actual execution, one of these sets will actually be consisting of corrupted nodes. So this is the so-called fail-prone system that is, then the protocol is prepared to tolerate failure of all the nodes in one fail-prone set. And with this, we can do consensus. This has been long Byzantine quorums in this model. You can also do this with cryptography. I'll talk about this later. This model is heterogeneous. You know? Not all the nodes are trusted in the same, but it's symmetric. Every node has the same trust assumption, right? You have to abide the same. If you participate in that system, you are assuming the boss is more important than the others, right? The node there, or you're assuming that these red nodes have this disruption power that they have. An important thing here that may come back later is the so-called Q3 property, a term coined by Hirt and Maurer. That means that no 3 of these possibly faulty sets must cover the whole participant set. So there's a couple of important assumptions here, namely that we must know the set of participants in order to really define this, right? There's also an important consequence of this, namely, if you have a set system such that no 3 of those subsets cover the whole space, then we have Byzantine quorum system, and from this we can do consensus. Interestingly, it's not used by any cryptocurrency. And here's another generalization now, and I'll talk about this a bit more later as well, which is taking the view before, where we had these heterogeneous failures, but all the nodes in the system use the same assumption. I trusted that these guys fail more likely than you over there. What happens now if we relax this assumption? And this is not our invention, basically, it's the invention of Ripple and Stellar blockchains that came with this model. They said, oh, you only trust the nodes that you know in a protocol. So some nodes don't even exist for me because I don't know them. So I do some voting based on, I listen to them, but I don't listen to others. And in Ripple and Stellar, they started to do that, Ripple first and Stellar later. And this is a scientific paper here where we went into this a bit more detail. So now you see, you should actually see 7 rings here, not only 3, but I did not have the space, yeah. And the trust assumption of the first node is the solid color. The trust assumption of the second node is the grid-shaped, grid-colored, and the trust assumption of the third node is the dotted, saying where the third node thinks others might fail. And we have a strict generalization of this Q3 property from before that we called, actually others before us called B3 property, where we can check whether this is still giving us consensus. Ripple and Stellar don't do that. Yeah? I'm going to talk about this later, but basically it means one of my faulty sets and one of your faulty sets and one of the faulty sets that we both consider to be faulty must not cover the space of all participants. Yeah? This is the generalization of this no 3 sets, and it's also the generalization of n bigger than 3f, right? Because previously we thought f nodes may fail, so 3 times f must not be n or larger. Okay, so these are models that have been pursued in a situation where, for actual chains or not, but in situations where we vote and we somehow know or seem to know the whole participant set. So it's a prerequisite to bootstrap the systems of these models that we know the set of participants. And this model here is actually a strict generalization in the mathematical sense of the previous models. There's a fourth model that has been used here where we don't have such strict quorums or such nice consistency guarantees. And I call this unstructured voting or probabilistic voting. The guarantees that we get from it are consequently probabilistic, not really as sound and secure as the ones from the previous systems. Now, since all these systems use cryptography, there is always, in a formal mathematical sense, the possibility that some of the keys get exposed, but we usually abstract this away and we pretend cryptography it works fine. In this model here, failure probability can be large. In this model here, we would just take the approach of randomly asking a few peers about their opinions on transactions. There are some chains, some of them are actual systems that have multi-million-dollar market valuation like Avalanche or also IOTA, where they use this idea. Interestingly enough, in this model, they don't build the usual kind of blockchain. And I assume here that everybody knows that a blockchain is a sequence of transactions that go into the ledger, like a sequence of decisions in a way, or a sequence of payment transactions where in each transaction sends coins from one to the other. And in this model here, they usually build a DAG. Now, DAG is jargon for a directed acyclic graph, which is more like a grid that evolves in one direction. I'll have one later. So these models have also been pursued, and consistency in these models is much less clear than in the first models because we don't have those textbooks that were just mentioned earlier, and you saw on the first slide a little advertisement for as well. A fourth model now would be stake. What is stake? In blockchain space, we have in blockchain space, we have tokens. We have the system, the nodes that participate in the network. get rewarded. They get rewarded in a cryptocurrency that is the native token of the system itself. That's the only reason why they participate, not just because they like to build a server and run it, because they get something back, yeah? Immediately monetary value. And an idea, so you'll see the proof of work at the very end, but an idea because immediately when Bitcoin came out, it was clear that this is going to waste a lot of electricity, a lot of valuable energy that could be used for better purposes otherwise. The stake is an alternative where we say how much you own in terms of coins or tokens in the network gives you a certain influence on the protocol decisions. You can see now that this the evolution from the votes to this, because it's another direction of generalizing, where we say, oh, if you have twice as many coins, you have twice as many votes. From any kind of Aktiengesellschaft, I don't know in English, but any kind of stock holder meeting, you know the situation exactly. Your vote is proportional to this. And there are a family of protocols, there are a number of protocols that use this model, and they're listed here for the early protocols of this kind that used the stake directly in the sense of voting. So they vote, but now you vote like the general meeting of the assembly with their coins. So it's a kind of oligarchy, yeah? And has own problems, but the Cosmos allows this, and the EOS and the NEO or earlier systems that started before the last two here, namely Aptos and Sui, are systems that just came out last year or this year that are built roughly with ideas that came forward from the DM cryptocurrency project at Facebook, because the engineering teams from Facebook left and they ended up at these two companies essentially, like the companies behind the Aptos and the Sui chain. Now, more. You cannot only do the stake-based protocols by voting, by using the stake to vote. You can also use the stake in the sense more of a lottery that determines your chances of being elected by the lottery. The proof of work in Bitcoin can be seen as a lottery in the sense that you're elected to produce the next block with a certain probability. And in these protocols, we make it explicit what is the probability, namely through advanced cryptography. For example, through the tool of a so-called verifiable random function, you can notice whether you are elected or not. You cannot cheat in there because the cryptography prevents you from cheating. Yeah? So you can recognize yourself without talking to others whether or not you have been elected. There are also other members where they talk to each other to elect somebody, but it's essentially a probabilistic election happening once per slot in such a protocol, and every 30 seconds could be a slot. And then this node in the protocol has the right or the obligation to produce the next sequence of transactions, so to extend the sequence of transactions according to the rules of the chain. The Ouroboros protocol family that is used in the Cardano blockchain with the ADA token and is basically the main member of this family. Now, some in the audience might object that, oh, didn't the VRFs come out with Algorand and Silvio Micali, who is behind, and the inventor of the VRFs, the verifiable random function cryptographic thing? Yes, that's true, but in Algorand there is an additional mechanism. This additional mechanism has been seen in other chains also, in other models, namely the idea that you elect a number of people, but then you elect them into a committee, and we still let the committee to decide some things, the committee do some things. And in this, I call them hybrid models and stake-based hybrid models, there's usually also the idea of penalizing faulty nodes that comes in. So if you're in this committee, then whoever elects you in this committee and you don't perform well, and in order to be in the committee, you have to invest some amount of your stake, some amount of your tokens. If you don't perform well there, or even if you would even sign conflicting messages, like if you would misbehave, right? Sign conflicting messages, like approve a double spending, like misbehave at the bank clerk, then your investment is lost. It's going to go to the majority of the other nodes who have the power to confiscate this from you because you are violating the rules. Yeah. This is now maybe a very popular family of protocols because Ethereum moved to a relatively complex combination of two protocols that are called LND goals and FFT Casper, and would take at least a couple of hours to describe if then I would fully understand them, but I do not, I have to admit, at this time. They moved, well, just to say that there are not as clean theorems on them as I would wish there be, or theorems that I could understand, okay? So these protocols, but also other protocols like Algorand, where you use the verifiable randomness, the sort of a thing that has also been called sortition, that you sort the nodes cryptographically, that is used to determine their voting power, makes them into a committee in Algorand. Yeah, there is more. There is proof of space and proof of delay. So I have to mention Christoph here, who was working with Shia and verifiable delay functions. Here, it's about some time resource that you're using and some space resource that you're using to influence the voting in the protocol. Some of these protocols come with usable guarantees in the sense that they are also storing your data. And the more you store for others, the more voting power you will have. Yeah, there's a coin, there's a chain called so Filecoin, right? It's listed here, uses a consensus of this type. It's not as simple as it looks like here, because also random choices and things happen there. You need to prove that you store a certain amount of storage. You don't want to disclose all the single bits that you do. You cannot simply send them around. So you have to do something smart and clever in a cryptographic way to prove that you're actually storing it. And then you have to add the time domain, because it's not enough that you prove you hold it today. You want to also be sure that you store this data over a certain time period. And so Filecoin and Shia are probably the most famous ones that I would call work in this model. So this is the model of proof of storage and also delay that I put together here, because the resources, I have not seen them decoupled in the literature and also in the wild out there. Number 9 is last but not least. This is what started the blockchain proof of work with Bitcoin, right? Proof of work, you do some totally useless but extremely parallelizable work, namely searching for the solution of a puzzle. And the solutions are found stochastically by multiple participants with certain probabilities that depend on your invested power, invested capital at the end of the day. And so it's a lottery that will make one node win this first, and that one will have the right to extend the blockchain and get a reward for this. It's called mining because you're actually searching a solution of the problem, of a hard problem, but it has no value to search that you're doing, right? But it's basically waste of work. I would not call it proof of work. It's waste of work for the sole power of keeping the chain secure. I think Bitcoin will never abandon this model, but Ethereum for the matter, you've seen earlier, it does not use this anymore. It has used this until September 22, but before it has used this. Now it has gone to one where power consumption is reduced by a factor 100 or 1,000. Yeah, and the Bitcoin blockchain alone has an electricity consumption of a small country like Switzerland, or maybe 2 Switzerlands nowadays. So don't underestimate this. Yeah. Okay, so these are 9 models in which blockchain protocols are currently operating. And if you know more, I'll be interested to hear about them an hour later. But this is a sort of a roundup. And now we go to phase 2 of the presentation, where we jump into certain models. And we start again at the beginning with voting, okay? We start with a problem that we have looked at in the threshold trust model. And there's one specific problem that we can answer nicely in that model, but not in other models, okay? And the question that we're looking at here is about order fairness. It's about attacks in decentralized finance. So DeFi is trading on chain. Blockchain is also a computer, right? It runs so-called smart contracts that are programs. If I am using a exchange that changes, I don't know, some token into another token, or real currency backed, so a token that is backed by real currency into a funny token, then this is visible on this blockchain. Especially also it's the case that when I send a transaction to buy a certain amount of tokens or to swap an amount of tokens for other tokens, this transaction is visible to the validators of the chain before it gets into the order, okay? And now, if I know that somebody is going to change 100 million or maybe a billion euro into a billion Swiss franc, this is going to have an effect on the price because people will see it. And this is the same here. So if a transaction becomes known, then members of the ecosystem can front run my transaction. They can put in another transaction, buying a lot of the token that I'm also going to buy, just immediately before, and then I also buy, and immediately after I have bought, they sell their tokens again. So the price will have increased even more because of the second of my transaction, and the others get a free benefit because they know my transaction has influenced the market. In traditional exchanges and markets, this is of course strongly forbidden. That's why in banks, you're really like, you can't just trade on the side a bit for you and then nobody sees it. You have to, you're not allowed to do that because you have all this extra side information. On the blockchains today, I say it's the Wild West. It's like lawless, right? What can be done is being done. So this is the front-running problem. That is a big problem affecting exchanges today and the efficiency of such decentralized finance products. People in an influential paper that have called it maximum extractable value, in the sense that you can extract value or minor extractable value, you can extract value from the innocent transactions. And there's a service today called Flashbots that will front run as much as possible. They take the view that if you can steal money from innocent users, you should steal everything and give it back in some sense. At least we control how it's given back to everybody. Not everybody agrees with this, but since it's possible to join this network as a miner in Ethereum, as a transaction validator, it's being done. It's being done on the majority of the transactions today. I don't know exactly in which form this comes back, but I presume that the Flashbot keeps a share for itself. So it's about exploiting innocent transactions because you know that the transaction is coming. It's like knowing this transaction will go in, so I create something that depends on it. How can I prevent this? Well, we go here in this work back to a assumption that has been introduced before by other Jules and Kelkar and others, where they said, okay, my transaction is obviously coming to the system, it's being propagated to the network, and if it arrives at all the relevant validators, and here it's important that we know the end validators, if it arrives at the validators before the fraudulent front-running transaction, then it should go into the chain before the fraudulent transaction, of course, because everybody saw this locally first. But it's not that we have this order ahead of time. It's just that every node in the system has a local order of receiving the transaction. You can see on the top left N prime and double prime and C prime, on the bottom N prime, and then also exactly the same order, and on the top right is N3 prime before N prime and then on double prime. And on the left, you have the clients that send out this transaction. Yeah? We assume that everybody who's validated in the network here sees all the transactions eventually, but maybe in different orders. So what can we do about this? Yeah? Can we not say that if a transaction is received by all of them before another transaction, we're going to put this out before the other transaction? Yes, we can say this. However, we cannot do this in every case because from voting and from personal preference expression, we know that we could create cycles. It could be an easy case where every message is before every other. Every input transaction appears before every other in as many cases around the network as there are. So here we cannot decide at all. It's called the Condorcet effect or paradox because there's no majority. Yeah? And so the notion that we are going to use here is one where we say, aha, apparently, if there exists such a cycle, this is a cycle, right? Because they point to each other, preference of the actual messages, which one was received before the other. If there is such a cycle, we have to just output them together. We have to output the C here in one basically position. We cannot say N prime was before N double prime. We just have to say they're all the same. And so defer the problem to the application. Tell the application, you deal with it. If they happen to be doing something bad or conflicting, then you might as well pay attention. So this is a scientific concept. It hasn't been tested out yet in the literature, but it's called block order fairness in the same sense. It's not a transaction block, it's outputting 2 of them or 3 of them together if there's possibly conflicts. How do we define the conflicts? So this is now our contribution from that paper that was last year at FC, at the Financial Cryptography Conference, where we say, let's count among the honest participants how many receive an M before an M prime. Yeah? So this is our number B of M and M prime as an input, right? They hear from the client. And then we want to prevent that if B M M prime is much larger than B M prime M, M goes into the chain before M prime. However, we cannot guarantee this for the reason before. And there is also asynchrony, like potential network disconnection, timing uncertainty. And there is also the faulty parties. The faulty knows they can always lie about what they have received first, can make up an arbitrary order. And so the best we can guarantee is this condition that you see here. If we have strictly more than 2F that received one before the other, then the order is restrained such that we must not put M prime, the one that had the lower number of preferences, before the other. It's a bit of you have to look at this for a moment until you understand what it is, but it's fine in this case to deliver the 2 together. That's what the protocol will do. And we can implement this on top of any kind of atomic broadcast protocol in the model I mentioned first, namely in the BFT model, where we know the N validators, and we have up to F less than 1/3 of N faulty nodes. Yeah. So this is a protocol, and there are some startups and then actually not only startups, but companies in the field that are thinking about implementing things like this. Yeah. So there's another result I want to mention here now. It's about cryptography, crypto systems. You know that typically the cryptography you're using is a public key cryptography. We can do digital signatures. Somebody holds a private key and publish the public key on the website. So I can sign with my private key and everybody can verify. Similarly, it's public key cryptography. Everybody can encrypt with my public key and only I hold the corresponding private key. If you now want to make a blockchain hold such a key, we need a tool called threshold cryptography. It's also called distributed cryptography. Essentially, we are going to distribute the key among the group, okay? And it's in textbooks, it's probably in your cryptography class, how to do this in the first model with threshold trust. Yeah, Shamir secret sharing, very nice algebraic methods, is being implemented in a number of blockchains, has been in production at some systems like Internet Computer Definity for a while already. What if we now wanted to do distributed cryptography with the model 2 that we had before? Remember, model 2 is the model where not everybody has the same voting power, yeah? But you have different voting powers. And we don't mean I have distinct points and I give you 2 points and I give you 1 point. That would be too easy, right? And also not efficient if we have a very fine subdivision of the points, of the influence points. So I want to do something that is more general, and it turns out from the literature we can do this based on these so-called generalized quorums. Let's look at what this means now at one of these generalized trust assumptions. In this system here that I'm showing, I have 6 nodes, okay? So if you remember the threshold case, threshold trust assumption, I cannot tolerate 2 because n has to be bigger than 3f. That means I cannot tolerate any set of 2. Yeah. But if I make a further restriction, because I just say, oh, the XYZs are close and might collude, and the PQRs, the lower half of the nodes, they might collude, 2 of them might collude. But it's never the case that one from the upper group colludes with one from the lower group. Then I can still do a so-called Byzantine quorum system because I have no 3 of these colluding sets that will cover the whole space of 6 participants here. So that's the example of this generalized quorum system according to the literature of Malki, Reiter, and Hirten Maurer that I'm listing here briefly. Here is the called Felix system F and corresponding quorum system. So the Q, each element of Q is a set that has the power to decide. When you look at this now from the viewpoint of cryptography, the question becomes, can we also use this kind of assumption for some cryptography? And the answer has been well known in theory, again, for years, if not decades, namely through tools that are so-called span programs, monotone span programs, or monotone Boolean formula. We can describe these access structures. And now what we are doing here in this research work, and there is the exact reference shows up at the back of the slides, and I'm going to make sure that you can see the slides later as well in some other form. We want to do distributed cryptography beyond the threshold. Yeah, we want to have digital signatures beyond this, and we're wondering how efficient is it? Is it horribly inefficient, or is it just a bit more expensive than ordinary threshold type distributed cryptography? So in practice, it's never been explored. However, there are some chains, and I will come to this later, like Stellar, that use sort of non-homogeneous trust structures like this one here. What you see here on the lower half of the slide is the trust configuration of one of the Stellar nodes. So you see here, I think it's 8 lines or 9 lines, and 6 of these lines have to be satisfied. And in each line, you see 2 out of, or 3 out of those on the right have to be satisfied. Yeah, so that's exactly what they also mean by asymmetric trust. They have nodes that are identified by these names, and they have a trust structure that consists of this. They declare the nodes that they trust through this form in a config file. And now what we do with our distributed cryptography work is we take such a config file, we turn it into a monotone span program generator that will output the linear algebraic model for checking this and for doing cryptography with it. Yeah, we assess that is a verifiable secret channel. It's a technical tool that's used inside distributed computing a lot, but it's a prerequisite for doing distributed signatures and thresholds, decryption, and common coins. Common coins means unpredictable randomness implemented by the system, but now according to this trust structure, according to this very trust structure here. And of course, when you do systems research, then you benchmark and evaluate, and you see how it performs. So it's, of course, taking a bit longer, and it depends heavily also on the particular access structure that you're using. But you see here, the black ones, the ones that are going higher up, they're a bit slower in terms of, it's not true in terms of execution time. We show here execution time by number of parties, but even if we go up to 100 parties, we are only a factor of 2 or 3 slower than, this is a normal ordinary, this is normal scale, it's not logarithmic scale, right? So if it goes up here, you can really see the factor. So it's not very slow. It involves sometimes Gaussian eliminations and matrix inversions for actually doing the distributed cryptography operation. Yeah. So this is an interesting thing that we've been looking into in this model. As I said, there's no practical chain that uses this kind of model in that form, but there are practical chains that use this asymmetric trust model. That's now going back. The third model I mentioned, where every node has its own trust assumption. Every node has their own, and this really started with Ripple. We went there and we started to formalize this a bit more mathematically. We do not end up with the same model that Ripple originally came up with, but with this model here, where we show on the right-hand side the quorum system of P. The blue node P has its own view of who could fail, how often, right? The blue node says, I'm never failing for myself. It's my assumption, of course. Yeah, and of course, in the normal protocols, doesn't make sense for the whole system to assume P does not fail. But for me, it makes a lot of sense to assume I never fail. Then are my neighbors, Q and R. I trust them. So I think maybe one of them could fail alone, the other could fail alone. And the 3 that are further away from me, the X, Y, and Z at the top, maybe 2 of them could collude against me. And now we could arrange these nodes in a ring like this. And we could say, you have the same trust assumption, but from your position on the ring, right? The ones that are close to you are more trusted than the ones that are further away from you. And so we get this kind of asymmetric trust assumption that every node has its own trust assumption. Every node trusts differently. Every node has its own trust assumption. And that's at the core of some existing blockchain protocols and some protocols that we also have developed that we call then asymmetric quorums. And if you're wondering once more, why should we do this? I have a couple of answers here. Why is subjective trust matters? Yeah. If you talk about food, then you can never argue about taste. Right? In the Roman Latin proverb here is that you cannot argue about taste because everybody has different taste. If you're into security operations, also in security research conferences, people can argue for hours whether an assumption makes sense or not, but you cannot really argue with convincing arguments. You can only pretend that you like this assumption better than another assumption. Yeah? So that's also what it gives you. And concretely speaking, in the blockchain world, Ripple declared early on that the node counts only the votes of those nodes that it trusts. It's a voting-based protocol. And in Stellar, it's sort of the same. Every node has a different idea about which nodes are important in the network, right? And if you're formalizing this in the sense of the existing quorum system literature, we get to this kind of model for asymmetric trust when we take the picture from before. If you take the union of all these subjective assumptions, we get the so-called asymmetric Byzantine quorum system, and we can do consensus and other nice things in this model, right? Threshold cryptography is yet an open problem in this model. I like distributed cryptography is yet an open problem yet. We don't have any very efficient schemes for this. Okay, I'm gonna skip over these things here now because it just shows that we just replace in the protocol where we count votes by determining membership in such an asymmetric quorum. Here, now, model 4 was the one that I mentioned where we sampled randomly some peers, and I think I have time to talk a bit about this one too, which is happening in the Avalanche blockchain. In the Avalanche system, they have what is called the Snow family of protocols. There is a metastable consensus mechanism. The idea is that if you are just letting a system evolve where every node queries some neighbors randomly for their opinion, in the basic case for binary opinion on whether this is in or out, and then you adopt a majority of what your neighbors are sampling, right? The idea is that through the random fluctuations from the sampling process, no matter which initial configuration you have, within, say, reasonable time, the whole system is going to go into this side. Every node is going to decide up, or every node is going to decide down, just by repeatedly sampling neighbors. And that's what is at the basis of the Avalanche protocol. That you have random sampling steps that don't require you to talk to the whole system, yeah, or to talk a constant fraction of the whole system, but a smaller number of nodes. How small remains to be seen. In the actual system, they have some constants, right? Here, I show a transaction graph, which is a DAG. You have transactions that point to previously occurring transactions on which they depend, yeah? And somehow, many of these unstructured voting protocols, and especially the Avalanche protocol, they build such a DAG of transactions, because if you process the transactions in parallel, as you can do in this graph here, T2 and T3, you can run on them in parallel. You can decide on them in parallel if they don't conflict, right? If they happen to conflict, we have a problem. So we cannot go here and include from T9, actually T4 is the culprit here. T4 would see that the two predecessors conflict. It could not go in like this. Yeah? It would not be improved. It would have to pick one side. And so they form, the nodes form such a DAG, such a graph on their transactions. They ask each others about their opinion in it. And here's how the protocol would look like. If you have then, after a while, you have a sufficient majority with the alpha answers that are positive from the transaction and so on, you can consider to be approved. They give special treatment for so-called conflicting transactions. These are the ones colored in yellow here, where the conflicting transactions have a higher approval thresholds. And sometimes you also go back in the approval, you reset these counters to 0. So we construct, and this is a research where the reference shows up here as well, we constructed the formal model of this. We extracted from the source and from descriptions what this protocol is actually doing, because there was no such description available at the time from the Avalanche protocol developers. There was also no theorem available, and what we discovered was a problem where it could be the case that you create a transaction down here that will point to conflicting transactions, and it can basically halt the network, right? It's like a denial of service. It will not be good, yeah? So we started to talk to the developers, and also at the same time, we tried to demonstrate the attack with the code. And we couldn't demonstrate the attack in the code because the developers told us that, oh, we know about this, we don't do what is in the white paper, we do something slightly different. And of course, that's what we discovered then. So we are back to square one, trying to prove more security for what actually happens in the protocol, but also for other reasons. This DAG protocol was abandoned by the Avalanche, and now they build a chain. They no longer build a DAG, which had to do with other reasons, yeah? But it's interesting because it raises other interesting questions that we are looking at it in work that is currently going on, right? Based on this work that came out last year. Okay, I think I have time for one more. So let me look at the proof of work, and it's not going to be long. I shouldn't really say proof of work here, but I should say any kind of resource. We have seen stake. Stake was a resource that has been used for consensus influence, right? You can vote based on stake and can probabilistically select on stake. You have these sort of longest chain protocols that will elect a leader to extend the chain with certain probability that depends on their stake. Also, proof of work is this small, right? And so we ask the question, can we have an abstract mode of what the resource is that gives us the power to vote in a longest chain protocol? And the answer is maybe, well, yes and no. We have in a work here that was also from last year identified 3 types of so-called resource allocators. So we have an abstract supply of resource, and the participants go to this cryptographic abstraction of a resource allocator that gives them a verifiable commitment to the resource, or a verifiable allocation of the resource that they can use inside the protocol. The idea is then to show that with one protocol and the abstract resource, we can explain how it happens in all those other protocols. Turns out it's not exactly like this, that with any implementation of the resource, we can use the same protocol, because essentially when you do proof of work, you cannot duplicate your investment of the resource. When you do the stake, you have multiple places where you can try. So it's not exactly the same protocol, but the protocols that we have come up with here and formulated here are relatively similar. So it allows us to better characterize what are the resources that must be, what are the features of resources that must be there in a consensus protocol, so that we can build a blockchain at the end of the day. Yeah, that's it. So no questions asked. Maybe now is the time for questions. Go ahead.
First one, in this diagram, I don't understand when in the role of information concerning
Okay, let me repeat the question so that the Zoom recording understands it as well. So you're asking, in the asymmetric protocols, how do we define consensus?
How
do we achieve it?
Yes,
well, with a protocol, right? We achieve it with a protocol like this one here. That's not a protocol yet, yeah. Here is something I have omitted. Namely, I've now said something about the nodes in the protocol. If you are using the threshold model, and then you look at an axial execution, they're all going to be, so let's say we know as an all-knowing observer which nodes are corrupted and which ones follow the protocol, yeah? Then we have a number of nodes that is corrupted. And if this is bigger than our failure parameter f, we cannot do anything, okay? And we cannot give anything to the honest ones, right? The remaining ones. If the nodes that are corrupted are F or fewer, then the remaining ones are honest, and they get the full guarantees of the protocol. In this execution here, as shown on the slide, there's a third category, and that's the honest, correct nodes that have the false friends, that have the wrong friends, yeah? They have made a wrong assumption that turns out to be such that in an actual execution, nodes in a set F were faulty. If I did not foresee that these nodes are going to fail, I'm correct, but I'm still naive. The other ones that has foreseen for the execution are called wise for this execution. Now, consensus we can guarantee only for wise nodes, and more importantly, we can only guarantee liveness if there's, say, a cluster, we call it a guild, of wise nodes that have enough decision power among each other so that they can actually make progress. Yeah? So this is the bottom line here, a set of wise nodes that contain a quorum for each member of the system. So, but it's very, there's other work in this line where we look into how to make, how to compose such systems. It's getting very mathematical, but also very interesting how the trust extends transitively, perhaps. Yeah, this was question number 1 of yours. 3.
And on the fair transaction ordering, in many blockchains, transactions are disseminated between nodes to gossip them as well. So basically, then for these kinds of fair ordering protocols work properly, the clients will have to broadcast their transactions without them gossip becomes again the point of that.
Okay, so you're saying in the low-level transactions before they go into so-called mempool are disseminated by gossip. That's true. So they would have to broadcast them. Now I have to ask you what you mean by broadcasting. You mean me as a client will have to send it to each and every validator I know and trust, so the hope that it goes there first. Huh? That is essentially what could be happening. We also see that on the other, what must happen, right? We also see that existing chains don't use this Byzantine F out of N failures model. So the model is perhaps more realistic for a so-called layer 2, which is a kind of input channel to main chain, right? If you want to be safe from front running, you have to send your transactions in through this safety preservation thing where they go in through the committee first, because it's inherently a committee-based thing where we count. And only then the exchange handles these transactions in a different way when they come out of this, because they're going to be secure or safe from the front running when they come through this channel. And then, but then again, of course, the problem poses itself within this committee that acts outside the chain. But this is a market, to be honest, this is a market sending things into that, like this. Yeah. I see there's some question here. I think this is maybe chat. Okay. I have to read here. It says, in regard to transaction order fairness, what is the viewpoint in general limit the transaction throughput of the ledger? As far as I understand, most notions of order fairness seek to establish some order related to the time. Yeah, but it's logical time, right? It's not when the transaction was issued, it's logical time when the transaction was received, right? And causal order, in practice, there may be transactions that require more timely processing than others. Well, if you require more timely processing than others, I'm not clear how to distinguish them from the transactions that are the front runners transactions, because they won't bring in their transactions at the first point ever. The interesting point here mentioned is causal order. This is another defense against the front running I have not touched upon, but this is maybe the more prominent even, where the system, the validator nodes, they hold a threshold decryption key jointly. This threshold decryption key is used to protect the transactions. So all the transactions that come into the blockchain are encrypted by the clients with that key of the whole system. So the ordering happens only on ciphertext. So you cannot establish validity while you are ordering. You can only then sort into a total order the ciphertexts. And when you have established this, you go for a round of decryption on what comes next. And then it becomes clear what this transaction does. So here you cannot influence by being cryptographically oblivious by not knowing the next transaction. Yeah, this is secure causal order. We called it in a paper from a long time ago. This is like cryptographic based front-running protection by ensuring the causal order is somehow maintained. Yeah, I hope this answers your question. Yeah, the priority fee market, I'm not sure. I'm not an economist, so I leave this to the people who do economic models, and I cannot really ask. I hope this answers your question. You had one more?
Yes. So
you mean here in the block order fairness?
Yes.
It's even the 2/3 majority.
Yes. So like rational, right?
Sure.
But how is it much different from actually going to person saying now to generally and every person when they do transaction they have to they say do the signature which you do as in the normal and it's not acceptable for the first.
Yeah, but would it eliminate the front-running opportunities? Because if I could happen to be one that is very fast, seeing very fast your transaction, I am approving it, or I'm holding back, but I see it, I get it with my friends approved earlier. That could still be in the model. It could still be possible, I think.
So this is something you're honest.
Yes.
The issue is the assumption that they're honest is hard to make because there's no way to prove that they're not.
Yes, it's too easy to cheat in that case. It's not something that is becoming evident because it's really about ordering, about local events that only you are knowing. And in a way that has been enforced in traditional markets, really observing what everybody has done, right? Like that at banks, you cannot have an account with another bank. If you are a bank employee, you have to put your money in the bank that is there, not in another bank. Of course, you can try to cheat, and it's becoming too obvious that if you're holding your money offshore or something. So this is indeed here but when you're touching on the rationality of the consensus, it's not so clear to me in this model. We are working in that model where we have either honest or corrupted ones, and I don't really understand how to formally model these types of protocols that are supposedly in rational models where we are not tolerating any collusions. You know, quite often there are colluding entities in the protocols as well. I mean, they happen also just because the mining pools act on behalf of many miners, and the mining pools even have exchange information behind the scenes where they're disseminating transactions over separate networks today. So for me, the most valued thing would be that this transaction reordering or the fair ordering comes as a secondary service outside main chain that will then feed into main chain. Other questions? There was at least one more here. Another question. Thank you. Other questions? Yes. Asymmetric trust, right?
I know through trust analysis, it cannot be possible with any other local trust. So we are like in a dead end.
If you're in a dead end, yes. This is actually one of the main ideas that we want to achieve with this research. We want to be able to say, everybody declares their trust assumption. We let the so-called B3 property to be evaluated. And if it's valid, we have a quorum system. We know if your assumptions in executions are satisfied, you're going to get consensus within your guild. The guild is in the next slide. But if there is, if this property does not hold, as I alluded to before, like one of mine, and one of our joint failed systems must not span the whole set of nodes, and we are lost. Yeah, we are lost. We cannot do anything.
This requires everybody can set in one process something locally, and then there's an equation of all the processes together.
Yeah, there would need to be this evaluation, all this common, even again, what you did not mention is what I did not mention at the beginning of the time of the presentation, that there is a common understanding of who is in the system, right? So we do have, and I want to just point this out here. I'm going to make the slides available on my homepage under the keyword WISP. Here in this model, we have this last paper here with somebody who works on Stellar, where we abandon the idea that every node knows what the set of participants is. Then we cannot evaluate the B3 property anymore. So this is kind of a different formalization again, but it builds somewhat of a bridge between the asymmetric model that I've just explained and the model that is used in Stellar, which has yet other features, to be honest, right? So it means that we don't start from this common assumption anymore that we have a set of participants, because we said this B3 property that generalizes from the quorums in a mathematical sense, we cannot have the case that 3 fail-prone systems cover the whole set of participants. But if your set of participants differ from mine, it's not clear how to define it yet fully. But it's very interesting. We can look into this more deeply. We're definitely doing that. We don't know. We don't know. Oh, well, no, you do, because you have participants you know. I have the participants I know. And if we happen to talk to each other, we always put a little list there of the participants I talked to, right? So the moment we have seen a message of each other or a signature of each other, we also know who your friends are. I know who your friends are. You're going to know who my friends are. And we can evaluate if we still have consensus with these friends or not.
Can you talk a bit about like models beyond this honor being set in?
Models beyond, you mean?
Like somehow modeling is kind of rational being seen in practice in running systems, well, not assuming that okay, certain rational
I don't know. No, I don't think we can assume those are rational, because it's slightly the objectives are very soon very different, right? I want to cycle through here through the model. So I go to the, so there's a paper we also looked at Ripple here that shows up because they're asymmetric. And this is the paper on Avalanche. I didn't want to mention this. I want to mention that here on the, this is actually not the paper. We haven't really worked much in the proof of stake or space, but we have a very nice survey in the form of a master thesis of the stake-based protocols. But beyond those models, rational models, I don't understand them so much, right? So maybe we can extend them. It's clear that from the range of 9 models I've put, all of them extend to rational phenomena in different ways. So if we start to add the dimension of rationality, we are in a different world, presumably. Because a Bitcoin miner is not going to misbehave because they have made so much investment into their mining equipment. If they would misbehave, they would destroy the market and they would make their investment worthless. So these are side effects that are always there, we cannot really ignore so much, right? So we'd have to build models of this. Some people have done that, but not in this thorough form, looking across all the families of consensus protocols, because probably would use different protocols then, yeah?
Yeah, thinking more about the direction of all of them. There it seems like the honest set is too far from to capture the problem.
In order fairness, it's not clear if you are.
All fairness, we first spread, we first on fruited transaction, and then we spread later. Then basically nobody knows what rank in the first place, a complement ordering, then it's maybe fair. Well, it's
yeah, it may be rational because you get some incentive for it, right?
Yeah.
And we have other work where we are now making people rational for actions to, and forcing people to be rational by looking at actions they do today from the consequences the action have tomorrow. adding a time dimension. That's also the way that can be done.
Not single handedly do the blockchains. You have to like, I see when I were design. Yes, yes. So there's something to be.
More questions?
Okay, good. No more question anyway. Take question. Yeah, thanks for the talk.
Again?